Hello, and welcome to the last event in our 2020 SAM webinars. My name is Darius Gite, and today I'll be presenting our PySAM workshop. So this is our list of SAM webinars for 2020. Our Introduction to SAM, PV Systems in SAM, and Battery Series webinars have all been posted to the SAM website. This is our second PySAM event. The first one, Introduction to PySAM, was from 2019. So for this one, we'll be revisiting some of that material, but then shift gears to new material with a focus on PySAM simulations. So this webinar will be recorded and posted on the SAM website at sam.nrel.gov. So since this is a virtual workshop, I'd like to try to make it interactive, which means questions and comments are definitely appreciated and encouraged. There's this question box in the GoToWebinar desktop application, so feel free to type it in there. My colleagues Paul, Steve, Brian, and Matt are all online as well, and they'll be typing answers in that app and bringing them up during the presentation. Otherwise, we'll answer them at the end. And the goal of this workshop is to be a resource to developers, no matter where you are with PySAM. If you're writing your own or a first simulation, working through the examples, if you want to share some of your experiences or approaches, or some specific problems that you've been running into. So feel free to type those in or bring them up when we have discussions. So these are the items that I would like to get through for the presentation portion of this workshop. The first would just be an introduction, like what is SAM, what is PySAM, how do we get started with PySAM, how do we initialize models, what kind of models are there, and then actually being able to run the models require a lot of information about the inputs and outputs. What do they all mean? So we'll be seeing how to get that module information. Then we kind of want to tie together those pieces and put them into a detailed PV battery commercial example. And once we're done with that, I'll just introduce some helper functions, which are a new feature to PySAM since last year. And then once we're done with those, we can spend the remaining time with your questions, or we can also work through some of the existing examples on the PySAM repo. So great, let's get started with the introduction. I assume most of you are familiar already with SAM, the System Advisor Model. But SAM is a free software that enables detailed performance and financial analysis for renewable energy systems. SAM models a variety of technology and financial configurations, but all of them have a very similar structure. For the technology module, you have inputs such as the weather data, the system specifications, and the system losses. And the output from this technology module would be the electricity production, as well as technology-specific outputs. And then those outputs are then inputs to the financial modules, as well as costs, compensation, and financing, and incentives. And the outputs from the financial models are techno-economic results, such as the annual, monthly, and hourly output, capacity factor, levelized cost of electricity, net present value, payback period, and revenue. SAM offers a variety of technology and financial modules. On the technology side, we have a variety of solar technologies. We have PV, the detailed and simple PV watts. We have high concentration PV. We have PV coupled with battery, concentrating solar power, solar water heating. Additional technologies are wind, fuel cell, geothermal, biomass, and our newest addition is marine energy. And on the financial side, we modeled distributed ownerships such as residential, commercial, and third party. We model power purchase agreements for single owner, equity flips, and sale leaseback. And one of our newer financial models is the merchant plant, which is a power plant that's participating in markets such as energy, capacity, and ancillary services. And we also offered the host developer and a simple LCOE calculator. So then what is PySAM? So PySAM is a Python package that enables you to run the underlying modules that make up a simulation in SAM. Each of those technology and financial modules are built up of unit modules called compute modules in the SSC or SAM simulation core C++ code. Throughout this presentation, I'll just be calling them unit modules to emphasize their role in a simulation. And in the screenshot from the NREL PySAM documentation website on Read the Docs is a list of these PySAM modules or unit modules or compute modules. And you can see the correlation between these and some of the technologies that I just showed in the previous page, such as biomass and geothermal. And on the financial side, we have the Equipart Flip and the cash loan modules, which go into the all equity partnership flip or all of the distributed ownership models. So in SAM, a single simulation is a process chaining together multiple unit modules. So therefore, the order that you run these modules matters because it's important what information needs to be passed from one model to the next. You need to run the technology models to produce the annual electricity production to be fed into the cash loan module, for instance. So in this screenshot, I'm showing a table that maps SAM configurations to the compute modules or unit modules. A SAM configuration, if you've spent any time in the SAM interface, are types of simulations that pair together a technology and a financial model. So the first two that show up is the biomass combustion with the LCOE calculator or the biomass combustion with a merchant plant. So I'll be referring to these as configurations. And each one of these has a set of unit modules that are run. So PySAM, as well as SAM's other software development kits for other languages, expose these unit modules so that they can be customized and embedded in software applications. PySAM, however, does not contain all of the features in the SAM GUI. A lot of the interactive functionality or tools, such as the layout designer in Wind or in CSP, the OpenEI load database, OpenEI URDB download functionality, that's also not in PySAM. PySAM wraps these unit modules that are usually run when you click that simulate button. So I just like to emphasize kind of what's the intersection between PySAM and SAM. So then for PySAM, we have the official versions, which are currently at version 2.1.4. And that roughly correlates with our SAM release with patch 2. Our development versions go up to version 2.1.5.dev3, and in here you'll find some of our newest features, such as single time-step battery, a new dispatch algorithm, and all of the changes from our develop branch in SAM. So these are all open source and available for you to experiment with, but the official release of this development branch will coincide with our newest SAM release targeted for mid-November. Okay, so for this workshop, I'm going to be working part of the time off of this PySAM Workshop notebook. It's available online if you wanted to follow along. That would be great. It's on our GitHub website, so it's github.com/nrel/PySAM. You can browse to the examples folder, and it's going to be this PySAMworkshop.ipynb. So are there any questions so far?
No, there's no questions, Therese.
Great, thanks, Matt. Okay, so yeah, let's just see how to get started. How do we install PySAM? First, you need to install a Python distribution. You can download Python from python.org, or you can install Anaconda, which is a Python distribution platform. PySAM requires 64-bit Python version 3.5 to 3.8, and it's available for most Linux distributions, Mac, and Windows. You can install the package from pip, PyPy, or conda using pip install nrel PySAM or conda install -u nrel, nrel PySAM, nrel PySAM stubs. So note that the name has nrel prefixed. This is to help distinguish it from a package called PySAM, which does something very different. And this nrel PySAM stubs is automatically downloaded when you use pip. And this stubs package contains type annotations that help your integrated development environment, or IDE, analyze your code and provide auto suggestions. It's really just like a helper tool. So I'll quickly move to this terminal here. And so you can see where your Python is installed if you type which Python. It might be different if you're on Linux or Mac, Windows. So we see here that I have Python installed from Miniconda, and I'll look at my version, and my Python is 3.7.7. And then pip list will show that I have nrel PySAM and nrel PySAM stubs installed already. So once you have the package installed, we want to know, how do we use the PySAM modules? How do we create models? How do we fill them with data? So for this, I'd like to turn to that notebook. So this notebook, again, it's available on the GitHub website. So model initialization. Each technology and financial configuration is composed of unit modules. Each module documentation is in this modules page on the Read the Docs website. So here's a list of all of the modules that are currently making up the SAM configurations. But we also have dozens of additional modules that do a variety of calculations. For instance, it has older versions of PV watts. It could do something fairly simple, like just read the weather file, or calculate the module model parameters given some module spec sheet data. And so when you click one of these modules, we end up on the page for the module. There's a short description of what it does. So PV Watts V7 is our newest PV Watts version. It doesn't do detailed degradation or loss modeling. And all of the inputs are listed, as well as some of its functions. So I'll go through these functions in more detail in just a moment, but we have this default, from existing, new, and wrap functions. These are how you create and initialize models. We have some functions such as assigning data, executing the model, exporting the data, setting the value or getting the value of a attribute. Next, we have a group of variables for the solar resource group. So these are variables such as solar resource data, which contains the direct normal, the diffuse irradiance, as well as the temperature and wind speed. You can also provide that data for a file. We have a lifetime group of variables that covers the analysis period. And then we have the largest group for PV Watts, which is the system design group. And here's where you can set the array type, the azimuth, and a variety of other system design variables. Every module has this adjustment factors group, which allows you to specify constant, hourly, or period-based adjustment factors, such as losses, for both the DC and AC side. And the final group in the list will be the outputs. So you can explore what kind of model outputs are available. Here we have a time series of the AC inverter power. We can also get just the annual energy as a single value. So
Hey,
that's an
Therese,
introduction to, yes.
there was a question about the difference between PySAM and SAM. So I thought it might be useful to take a minute just to open a PV Watts case in SAM so we can see the inputs and outputs as they're presented in the user interface and compare them to those ones that you just showed us.
That's a great idea, thank you. I'm gonna open on SAM this PV Watts technology model with no financial model, so we can just focus on the PV Watts inputs. And so here I have, let me go back to the top here. So we have this location and resource page. This roughly corresponds to the inputs that are in the solar resource group. So here in the GUI, there's a nice library loader, but it is just like a helper for putting in the solar resource file. It's a helper for putting in the solar resource file, but that's like a SAM UI feature that is one of the many features that aren't available in PySAM. So here you have like the ability to kind of browse through the properties of these files, and that's not going to be something you can do in PySAM. For the system design group, you can kind of see that there's a system size, there's a module type, there's an array type, so that the names are different. So it requires a little bit of deductive work, I guess, but the array type here is also called array type. The system nameplate capacity would be down here in system capacity. The DC to AC ratio is similarly named. And then there's this breakdown of losses in the GUI. Whereas in PySAM, there's only a single loss value. So you'll see that very often when you're comparing the GUI with the PySAM unit module, is that the GUI will do a lot of work to add a resolution to the inputs, which is what it's doing here. It's helping you break down losses. It'll also add additional constraints to make sure that you're not entering a value that doesn't make sense. And but there are also features that are available in PySAM that aren't necessarily available in the GUI. And that number of features is a lot smaller. Yeah, was that, do you think there's more I should go into about that, Paul?
That's helpful. Yeah, I think maybe show the inputs browser for a second, so to list the variable names.
Oh yeah, great idea. So a nifty feature in the SAM GUI is the inputs browser. This is going to show you the variables that have the exact same names as the compute modules. And so from here you can see our array type earlier. This is our fixed open rack. And then that will help you match up to the PySAM variable.
And you got to that from the file menu, right?
Yes, that's file and then inputs browser. You can also toggle this view menu and select show calculated variables. And this will display variables that are modified by the UI. Okay, so hopefully that was helpful. Thanks for the question. So now, yeah, getting back to just how do we create these modules, we'll definitely spend more time going into figuring out the data and doing a comparison for the detailed PV model between the SAM and PySAM, for example. So there are 4 ways to initialize a model. First, you have to import the module using import pysam.module name. And there are 4 ways to initialize a model. You can use new, default, from existing, or wrap. So for this demo, I'm going to use the PV-Watts v7 and utility rate 5 modules. So I'm going to import them. The new function creates an instance with empty attributes. So it creates a model and it has no variables and all of its variables have no values attached to them. I'm going to run this code and it's going to show me when I export the data that all of my variable groups are empty because there's no data. The type of the model is PV Watts V7. So this is not as useful if you have a lot of data to run a model, and oftentimes you do have a lot of data that you need. Entering that data with assignment statements such as new model dot solar resource file equals some string, that can be tedious. So one way to get a full set of data is to load the default setup, which is the same as in the SAM GUI. So a module's default values are unique for each SAM configuration type. So for those of you who've spent any time in the GUI, you'll note that when you first start up a SAM simulation, there are already default values provided for everything, and these will change depending on the configuration. Like the default PV size will be different for a residential case versus for a single owner case. So all of those values are also available in PySAM, and you can access those with this default function by keying into the configuration name. So these default configuration names are case insensitive. A list of the options can be found on the PySAM documentation page right here. And these, again, just correspond to the available configurations in SAM. So options we have are the PV watts with battery for commercial, or just PV watts with no financials. You can access that same list using this help function. And so here I'm just going to choose the first one, which is PV coupled with fuel cell for a commercial owner. And now when I export this model's data, I see that I have quite a few variables pre-populated, such as an inverter efficiency of 96% and 215 kilowatt system capacity. So this is good if your situation is close to the default. Often, however, this is not the case. When your setup is significantly different than the default, you can enter the data using SAM and save that data to a JSON file, which can then be loaded by PySAM. You can then modify and use the data in PySAM as needed. So this is shown to import a case from the SAM GUI page on the Read the Docs, and it was also a subject of last year's webinar. A new way of creating a model is from existing. So when running more than one unit module in a sequence, data needs to get passed from one to the subsequent models. For example, a technology module's analysis period and generation profile, gen, are inputs to the utility rate calculator in order to calculate the annual energy value, which is the energy value in each year of the analysis period due to the electricity bill savings. So this function from existing is used to create a model that shares the underlying data with an existing model. And this new model can be created with default values if a default configuration name is provided, similar to default. So here I'm working with the default model that we created above. And then I'm using the utility rate module to initialize a new utility rate model called shared model. and I'm going to have it use the same default configuration as above. And now when I print the analysis period of both my PV model and my utility rate model, I'll see that they have the same value, which makes sense because they're using the same data. And likewise, when I change the analysis period in one model, that's reflected in both models. So all variables and their values, including inputs and outputs after they're generated by model execution, are shared between models linked by this from existing function. So when the PV model below is executed, its outputs will automatically be available to the utility rate model. So order of execution matters. Simulation data is passed between unit modules. When the name of a unit module's output is the same as another unit model's input, such as gen, the group name doesn't matter, and those can be different. So here I have the PV model. The generation profile doesn't exist yet because I haven't simulated it. So then I can't run my utility rate calculation. It gives me this execution error that says an invalid number of generation records, or of gen records. So what I have to do instead is I first execute PV and then the utility rate calculations. So I just provided it this weather file. I run execute. I'm looking at the first 10 entries of my hourly generation. And then I run my utility rate calculator and I look at the annual energy value for every year of my analysis period. The fourth way to create a model is using this wrap function, which creates a model from the PySSC data structure. This allows compatibility with PySSC, which was our older Python wrapper. And this Python wrapper is still distributed with PySAM, so you can access that through PySAM. This function is primarily used during data import from SAM via JSON. So this import feature is covered in the webinar as well as in the documentation page linked here. But PySSC is imported in this way. It's this class that you can use to create an SSC data structure. This SSC data structure holds sets of variables and their values. So here I've set this data structure to contain a new variable called analysis period, set to 10. And now I want to create a PV watts model using this data. So that's what this wrap function does. It wraps this data and takes ownership of this PV det. And so when I export the data from my PV watts model, I see that it's empty except for the analysis period. So that is the introduction for model initialization. Are there any questions regarding that?
Aren't any questions? Oh, here comes one. Here's a question. It's how do you set parameters only for shared model without changing them in default model?
If the name of the variable is the same, as in our example here, then you cannot. If you want to have them use unique version or unique data, then you shouldn't use this from existing function. Instead, what you should do is create a separate model. And then pass in data explicitly. So you could say your shared models lifetime dot analysis period. You know, something like this. This would be okay. They would have different analysis periods. This is not recommended. You should have a consistent analysis period in your technology and financial models, because part of our time step calculation is oftentimes dependent on consistency. There are other potential gotchas as well. But you know, for a case where this isn't important, then this is the recommended way to pass information is explicitly. Yeah, thanks for the question.
Here's a couple more questions coming here. Can it show a block diagram for the design system?
No, we don't have any, I guess, visualization features like that. Right now, there isn't, I would say the process is pretty implicit. Once you've used this from existing function, they're all going to share the same data. So it's really almost like a Venn diagram rather than like a flow chart, or flow sheet, I guess. The only place where you can enforce the order like you would in like a flow sheet is really the order in which you execute the models and pass information.
Thank you.
Yeah, good question.
And then another question is about if I save a JSON from the SAM GUI, how do I open it in PySAM?
Yeah, so that's what this page will walk you through. Once we've exported that JSON, then in Python, you'll load it into this dictionary. And then once you've loaded it into this dictionary, there's this PySSC function called dict to SSC table, which will take that dictionary and pull out all of the variables that are required for a given unit module. And those unit modules variables will be pulled out into this data structure, pvdat. And this data structure we can then give to this wrap function. And this wrap function will return a PV-Watts model that we can then execute. So here we run execute. And you'll note that we have to do this for each of the unit modules. So here we read the data structure specific to the PV-Watts and the grid and the utility rate. And then we wrap the first one. We wrap the PV data to create the PV-Watts model. We'll create a grid model that is sharing the same data as PV. And then we'll do the same for the utility rate and for the cash loan. And then this is kind of an inelegant way, but this is, I think, the easiest way to get the data is you assign to the grid model the variables that are exported from a new model that is produced from the wrap function. So that's kind of like a mouthful, but yeah, I encourage you to take a look at this.
And then there's another question here. Can we access the supplier catalog parameters of component through PySAM, for example, for PV?
Oh, do you mean like the cost model breakdown? Not quite sure what that means.
Yeah, I think it might be how to access maybe a list of input variables for a module.
And can we access it from PySAM?
Yeah,
Oh, a list of modules.
I'm not sure if it's a list of modules or a list of parameters for a given module.
Okay. So yeah, this is the list of all the modules in PySAM. There are several ways to look at the inputs for each of these modules. This is just one example. Later on, I'll show the SDK tool, but also you can click on the link to the source code, and their source code has these var info tables that tabulate all of the inputs and requirements on these inputs. But yeah, I will go a little bit more into detail about this later on if that's
Oh,
what the question's about.
yeah, and there's a clarification here maybe that it's a accessing the component libraries like the module library and the inverter library
Ah,
for the
gotcha.
PV. Yeah.
Gotcha. Yeah, that is only a UI feature. What you can do is go in SAM, you can go to the SAM GitHub page and go to where those files are being loaded from by the GUI and pretty much do that through Python yourself. So I can add this to the PySAM Workshop, so you will have like a direct link to it, but it'll be in runtime and then UI, no, not UI.
It's in the libraries folder, I think. Deploy
Libraries. Oh,
libraries.
deploy libraries. There we go. Thank you. So here are the libraries of the CEC modules. And so you can, download this, read the CSV into Python, and then load up these parameters into the CEC module group in PySAM. So that would be the CEC performance model with module database group. And these parameters to the module model, such as alpha of the short circuit current, beta of the open circuit voltage, etc., can be loaded up from this data. Great, that's a good question. I guess I'll just move on in the interest of time, but we'll definitely stop for questions in a moment, or not in a moment, after this next section, which I think would be broadly useful, but it's pretty clear that there's a lot of information and data and functionality that is in PySAM, but it might not be in PySAM if you're very familiar with the SAM GUI. So definitely still the easiest way to understand PySAM is to work with the GUI, is to explore the user interface, because that, first off tells you what technology and financial simulations are available. It also categorizes the inputs for you, like we were looking at earlier with the solar resource system design. These UI pages help categorize the inputs that are sometimes the same category as used by PySAM, such as that CEC performance model with module database. The GUI also helps clarify what are the inputs data requirements. Is it a float? Is it a string? Is it an array? And a very important part is that it maintains consistency among interdependent inputs in the GUI. And so the UI will highlight and alert users to inconsistencies between, interdependent inputs. One example is if you gave a negative number to something that is like a physical dimension, so that's like maintaining a constraint. But something else that is a really popular feature is that it runs all these calculations for you, such as the cost model. The PV cost is calculated automatically in the GUI. I can show this. Right here, as using cost multipliers for the module size, the inverter size, and it breaks it down into this balance of system equipment, installation labor, and so forth. And it provides this layout for you to adjust this total direct cost, which is then summed with this total indirect cost and becomes this total installed cost. When you are talking about just the PySAM input for the unit module, which is here the single owner module, the single owner input is just total installed cost. So it doesn't break any of this down for you. It doesn't help you compute these absolute values given these multipliers. So this is like a SAM feature that helps you maintain consistency between the system design and the cost model that isn't available in PySAM, and that's something that you'll have to do yourself. And so going back to our presentation, PySAM requires users to maintain those input consistencies. So you have to make sure that you make changes in the correct order, right? So you would change the system size first, and then you would change your total installed cost, and also monitor and understand how the data flows from one unit module to the next. Since all of this is handled behind the scenes in SAM, it's not often clear that it's not available in PySAM, and this is something we're actively working towards, is moving that functionality out of the GUI into a place where PySAM can also access that. And there's also documentation for how to be aware of these variables that I'll get into. Okay, so yeah, getting module information. In SAM, a set of input pages is loaded to present all the inputs that are needed for the whole simulation. A list of all simulation configurations and their unit modules in order can be found on the PySAM documentation site under SAM simulation configurations. So here I'm showing the biopower LCOE calculator in SAM, and on the right, this is how you would recreate it in PySAM with the biomass grid and LCOE FCR modules. And for each unit module, the PySAM inputs are categorized into groups. So here we have only two groups, the biopower group and the adjustment factors group. And the adjustment factors group is common to all of the technology groups. So really there's just one group. Sometimes these groups correspond to the SAM UI pages, but sometimes they don't, as in this case. But when they do, it's really helpful to just pull up SAM, open a case with that configuration, go to the UI pages and look for the variables there. It's really helpful to open the help menu that is in each of the pages on the GUI that helps explain what all of the variables do. That inputs browser that Paul mentioned is also very helpful. And other ways of accessing these unit module inputs and outputs is through the SDK tool. The SDK tool comes with the SAM download, and it allows you to look at the inputs and outputs, and as well as run simulations. And the other way to do it is to, click through to the source code and look at the variable tables in the SSE source code. So once we look at the variable table, the variable table contains information about the variable type. Is it an input? Is it an output? What's the data type? Is it a string? Is it a number? It contains a label, the units, some meta information when applicable, the group, so that's the PySAM group name, contains whether or not the variable is required, what constraints apply. So here we see that it has to be an integer, it's min and a max, and then also any UI hints. And the source code is also really useful for just figuring out what a function, what an input is used for. And so you can take a look there. If you're, getting some error, you can look up that error message and say oh, is there something obvious that I can find from this code, or try to understand that better. So those are some ways to get unit model input information. And again, I kind of want to go back to this input consistency issue due to the differences between PySAM and SAM. In the PySAM documentation, you'll note that some variables have these lists with this variable may need to be updated if the values of the following have changed. This is an alert that there's some connection between the two variables in the SAM GUI that may or may not apply to your specific case, but this interdependency is something to watch out for. So in the example that I have here, the inverter count input to the detailed PV model, PV SAM V1, this is the number of inverters, and the detailed PV SAM, the detailed PV model uses, an inverter model that models the input and output voltages and powers. And so if you change your inverter parameters, or you change your module parameters, you may have to change the number of inverters in your system design. So that's basically what this is saying. Where did it go? That's what this is saying here. It's saying if you change the number of inverters, make sure that your module parameters are consistent. So 6-par IMP, 6-par VMP, 6-par VOC, like what are these? We can go back to our documentation and try to find where it's listed. Okay, so we see that it's part of this CEC performance model with user-entered specifications. And that corresponds to this module model here. So the VMP is the maximum power point voltage, IMP is the maximum power point current. And so it makes sense that if you change your module, you may have to, change the number of inverters that you're using. And this dependence is mutual. If you go to the 6-par IMP documentation, you'll see that it depends on the inverter count, but it also depends on your subarray design. And so in SAM, this is automatically handled for you with the system design feature. This will alert you to cases where your string voltage or power is mismatched. But in PySAM, this is up to the user. So are there any questions on this topic? I know it's kind of more just like a warning than anything super actionable.
Nothing pending at the moment.
Okay, great. So now we'll go to the detailed PV battery commercial example.
Oh, sorry, just one just did come in.
Yeah.
Is there a way to get the 6 parameters from the CEC computed based on a new data sheet? So that's more of a detailed question about the coefficient generator module.
Mm-hmm. Yeah, exactly. So we have a unit module called 6-par solve. And this is what's also used in the GUI. And this allows you to calculate the CEC 6-parameter module parameters from manufacturer datasheet variables. So our inputs here are, the IMP, ISC, etc. And then our outputs are the parameters to the CEC module model. Yeah, thanks for the question.
I don't see any more, so I think we can continue. Thank you.
Okay, thanks, Paul. Okay, so our example, we'll be working with the detailed PV battery and commercial owner case. And this problem is going to use a set of PSM weather files for different years and calculate how the average net present value of the default detailed PV battery commercial owner system changes with the size of a 4-hour battery. So I'm going to run the system for all of the 21 weather files I have here from 1998 to 2018 to calculate the average MPV and see how that changes depending on the size of my battery. So I guess how I would start is figure out what unit modules I need. And then the ones I need are the detailed PV model. This one has the battery integrated already with it. We have this grid module that enforces interconnect and curtailment limits. We have the utility rate 5 electricity bill calculator. And then finally, the cash loan module, which is a financial model for residential and commercial behind the meter projects. It also helps compute the cash flow. Again, we can look at the UI pages and see a pretty good mapping to the PV-SAM V1 groups. This will help us locate our inputs, but we can see like the solar resource group, losses, lifetime, system design, shading and layout. For the module page, there are several module models that we offer. For the inverter group, on the inverter page, we have several inverter models, and then also some battery groups. Okay, so now that we kind of have a lay of the land, we can take a look at the code. Okay, so yeah, just to start, I'm going to import all of the unit modules. I'm going to print out the version that I'm using. And then in this code snippet, I'm getting all of my weather data, loading it up into the data version. So I have all of my files saved in this folder. And then I'm going to load them all up using this helper function. The reason I'm loading the data from file into dictionaries is that I'm going to be running many simulations for each of these files. And it's a lot faster to simulate on data that's in memory versus having to reread from file over and over again. So this is a really useful tool for cases where you're running a lot of simulations. It also allows you to, query into the data right away, so I can determine that I have some number of steps per weather file. So then I know if it's hourly or sub-hourly. And then I'm going to initialize all my models first. So the default configuration type is the same for all 4 unit modules. They're all using the same data. And then I'm just going to adjust some of the settings. For speed, I'll change the analysis period to 1. For the battery, I have to make sure that the room temperature inputs have the same time step as my weather files. And I'm just going to set it to use, set the battery to use the peak shaving algorithm. So when I run this, it goes and tells me that there's about 17,000 steps per year, so it's half-hour time steps. And I also, as I mentioned before, the cost calculator is not included in PySAM, so I just made up a dummy one right here. It's basically a linear combination of my PV and battery sizes and returns what I will call it the total installed cost for my, given these 3 components. And so this is the bulk of the problem. I'm selecting a range of battery powers from 10 to 90 in steps of 10. Sorry, 10 to 100. So it'll be 10, 20, ... 90. I set my battery capacity to be 4 times the power. And here I'm using another helper function, which I'll get into. But this helper function will help me adjust all of my PV-SAM V1 battery inputs so that my battery capacity and power is what I want it to be. And this is also adjusted. This is the voltage. So this is a feature that's available in both the GUI and in SAM. It just allows you to type in some battery size and the cell level battery inputs, such as the number of strings, and the number of cells per string. All of those are adjusted automatically for you. So now that I've sized my battery, I will run the simulation for all of the 21 years of weather data and calculate the average MPV. So since I'm basically working with a default, I'm not doing a lot of data assignments. All I need to do is set my data, and all I'm looking at is the total installed cost. You know, in reality, you'll probably want to look at different O&M costs, maybe different incentives. For purpose of demonstration, we're just looking at the MPV and how that changes with the size of the battery's performance effect on the generation and the cost. And so when I run this, it's going to print how the average MPV changes with respect to the battery size. And we see it starts negative, starts to get a little bit better, around 40 kilowatts, and then starts to decrease again. So for those of you familiar with the SAM GUI, this is a combination of the parametric tool and the stochastic tool, and is a feature that you wouldn't be able to do just in PySAM, or sorry, just in SAM, but you can do with PySAM. So yeah, any questions on this?
There aren't any outstanding ones. And nothing's coming in yet, so.
Okay, great. So the final section of this presentation is helper functions. So these are Python functions that you can use within your code. Oftentimes, they were imported from SAM. So there's two categories we have right now. One's resource tools. We have, these are functions that help convert data from one format to the other, or at least the first three are. The first one will convert SAM CSV files, SAM solar resource CSV files, I should say, to solar data. So it converts a CSV of solar resource data into the correct format for use in PySAM, PV watts and PV SAM V1. The second function is very similar, except it does that for wind data. It loads up a wind file and then converts it to the wind resource data. And then you can use that directly as wind resource data in wind power modules. The third one is for utility rate information, and it converts the utility rate database API version 7 response into utility rate 5 inputs. And then the last resource tool is this fetch resource files. This was a contribution, and this one is a convenient downloader for NSRDB and WinToolkit data. The other category of helper functions we have is this battery tools, which I have demoed in the last section. But the battery model sizing function modifies a PV-SAM V1 or battery module model for some desired power and capacity. So for these functions, there's tests and examples using them in the PySAM GitHub page. So if you're interested in how to use these, you can take a look there. And that concludes the main things that I wanted to present. So thanks everyone for the questions so far. And yeah, welcome any more thoughts or questions, comments.
Here's a question. When will the beta of a new release be ready? I want to try the battery model for a single day.
So you can try that already using this development version 2.1.5.dev3. So you can take a look there. And the way you can run that is you can go on this dev branch, take a look at the tests. Oops, wrong one. And you can take a look at this test here, which is running this battery stateful, which is a single time-step battery model.
Sorry,
So
Doris.
yeah.
Oh yeah. Okay.
Oh, so yeah, so you can access that right away with pip install nrel PySAM equals 2.1.5 5.dev3.
Okay. There's another question here. Oh. Could you show that pip command again?
Oh yeah. Oops. So it's double. So yeah, now I've just upgraded my PySAM version to 2.1.5.dev3 from 2.1.4.
Okay. There's a question here about the simulation time step. It says, can
Oh,
I
and I
set?
should
Oh,
also
sorry, go ahead.
mention. Oh yeah, and I should mention that the battery stateful, which is a single time-step battery model, does not come with the dispatch algorithms. So what I mean by that is when you run the battery unit modules, you can choose like a dispatch option such as peak shaving, look ahead, peak shaving, look behind. All of that dispatch capability is not available through the single time-step battery. Yes, okay. Paul?
Yeah, there's another question here about setting the simulation time step. It says, can I set the simulation time step, for example, 1 hour, 30 minutes or smaller?
1 hour, 30 minutes. For all, okay, so there's 3 modules where you can kind of set the time step. So that would be the battery stateful one, and then the PySAM v1 development version. You can specify the timestamp on your data, on your solar resource data, and there's no limitations. Well, there are limitations, but you can, give your solar resource data at 1.5 hour intervals if you mark that data, correctly. So you would say, like, my first one is, hour 0, 0 minute. Your second one would be hour 1, 30 minute. And that's the way that you set your time step, is through the solar resource data. In this development version of PySAM v1, you don't have to give a full year of data. So you can just give, 1 or 2 time steps if that's what you really want to do. So this, we're calling it like the single time step feature, or the variable simulation length feature. That's available for PySAM v1 and PV-Watts v7.
So the for any model that's not either the
Yes,
development version of PySAM v1 or PV-Watts v7, or the new battery stateful model, the number of records in the weather file determines the simulation time step, right?
exactly. And they are usually, can't be more than, the time step can't be less than 1 hour, less than 1 minute. And I don't know if it can be more than 1 hour.
Yeah, I think there has to be a multiple of 8760 records, so it'd be from 1 minute to 1 hour.
Yeah. For all unit modules except for the development version of PySAM v1, PV-Watts v7, and battery stateful.
I'm also watching the list of participants. If you raise your hand, I think there's a little hand symbol that you can click to raise your hand. If you raise your hand, I'll unmute your line if you'd like to ask a question by voice instead of typing it. Or if you have a project that you've been working on, we'd also be interested in hearing about that. Or if you have a specific problem that you're trying to solve, that this is an opportunity to get a little feedback. So no questions yet or hands.
Well, I guess it's super clear now.
Here's a question. Do you know of any PySAM developers we can hire for a project?
There are several people using PySAM. I don't know if any of them are looking for, I'm not quite sure, like, if they can be contracted out or what not. I don't know if, Paul, do you have any thoughts on how that might work?
Yeah, we don't have a list of either for SAM or PySAM, a list of, consultants. There may be some other folks on this call that might be in a position to provide that service. You could post a question on the SAM forum. That might be a way, or maybe ask. I don't know if there's some communication method on the PySAM GitHub page, but you might try reaching out to folks through those channels. But we don't maintain a list, unfortunately. Okay, here's a question. Do I need to install PySAM, but could you show how to change the temporal resolution for a battery project to a 1 second resolution in PySAM? I'm trying to estimate battery degradation for a frequency control application. Batteries need to respond to frequency deviations every second.
Sure, I feel like I've made such an example. Let me just look for that. Sorry, I can do this. Okay, so here's a piece of code that is using the battery stateful model. We import that as battery. The list of inputs to this battery stateful model is pretty small. It's literally just the physical components of the battery, as well as some like control variables, such as what's the mode that I want to control it by. When I select 1, it means I want to give it input power. If I select 0, it's by input current. But in here, we are not doing that. Then you set the time step in units of hours. So here we're running it second by second. And then I choose the chemistry type. Here, 1 is lithium ion, 0 is lead acid. I can set up a size. So I'm saying the energy is 10 kilowatt hours, voltage is 500 watts. Initial conditions of state of charge, voltage model parameters. You can grab these from the UI. So those voltage parameters correspond to the parameters to this voltage model. You will have to use the inputs browser to get the voltage parameters. Let's see. Okay, so yeah, here's some of them. Here's battery nominal voltage and also nominal voltage default. So that's VNOM here, VNOM default. There's also some thermal parameters that is going to be displayed in the thermal section. So this table here is this capacity versus temperature table. And then here are some heat transfer coefficient, heat transfer model parameters. And these are the lifetime model parameters, which correlate to this page. And then we also have some losses and replacements. So I have listed these parameters in a dictionary. After I create an empty battery model, I go ahead and load all of these parameters into my model. So I set the value, and then I run the setup function, which is required for all stateful modules, and then I can run execute. Oh. Yeah, so then when I run it, I am printing this state pack. So that's basically the state of my battery pack, and I'm looking at all of the data that's exported from just this group. So I can see that my current is 0. I can charge up to 3 kilowatt. No, sorry, 3,000 amps. Sorry, and discharge up to about 3,000 amps. My operating power is also 0, which makes sense if my operating current is 0. I have about 1700 kilowatts that I can charge. So in my next time step, the maximum power that I can charge is about 1700. This is for the max discharge power in the next time step. This is my capacity, and my capacity max. So that means my state of charge is 50. I have the temperature of the battery, the temperature of the room, the voltage of the battery pack, how much heat was dissipated, and then These are other parameters such as the last index, what's the loss percent, and the number of replacements that have happened so far. Oh, yeah, here I have some more stuff as well. I don't know if, but yeah, I'll just, see if there's any questions or comments to that.
Just thank you, and also where is that file? Is that example accessible?
I think it might be on the webinar page. Let me see. Not webinar page, but yeah, we can post it on the SAM website, or I'll post it on the PySAM examples page. So it will be added to this folder here, the examples folder that's inside my development branch.
So any other questions or hands raised? I don't see any at the moment.
Okay, well, thanks everyone for your attention and your questions. I hope this was, a useful workshop. And please do follow up with us if you have any questions or comments. The SAM forum is the best place. That way, your questions are and our answers are available for future use, and it kind of builds up a repository of information. If you have any sensitive information, feel free to email SAM support. And yeah, thank you so much.
Great, thank you, Doris, and thanks everyone, and have a great rest of your day. Goodbye.